The science behind why we're facing a solar-triggered magnitude 8 plus earthquake. Could the massive hole in our sun's atmosphere trigger the next catastrophic earthquake within weeks? Stay with us as we reveal how solar scientists have identified patterns suggesting we're approaching critical danger zones based on 8 months of anomalous solar behavior. The clock is ticking on Earth's next major seismic event. We are currently experiencing the longest drought of magnitude 8 plus earthquakes in recent history. Over 3.5 years have passed since the last one struck in August of 2021. This isn't just an interesting statistical anomaly. It's a concerning departure from the expected pattern where we're typically experiencing at least one such event annually. This extended quiet period doesn't mean the risk has diminished. Quite the opposite. In the unforgiving mathematics of seismic energy, this delay suggests pressure has been building across multiple fault systems worldwide. While traditional seismologists focus on ground-based measurements and historical patterns, a growing body of evidence points to an unexpected influencer of earthquakes: our sun. Right now, a massive coronal hole nearly 8 times the size of Earth is completing its 8th rotation on the sun's surface since first appearing in October 2024. This isn't just any solar feature. It's a persistent structure that has grown progressively larger with each 28-day rotation, now spanning nearly a quarter of the visible solar disk. What makes this current situation particularly alarming is the timing. This enormous coronal hole is expected to become geo-effective directly facing Earth. Due to its unusual width, spanning from the sun's equatorial region towards its southern pole, the Earth will remain under its influence for approximately 7 days. This extended exposure period significantly increases the probability of triggering the seismic mechanisms we've observed in previous earthquake solar correlations. The connection between these solar features and earthquakes isn't merely theoretical. When we examine the catastrophic magnitude 9.1 earthquake that devastated Japan in March of 2011, creating the Fukushima disaster, satellite imagery reveals a remarkably similar coronal hole was positioned directly Earth-facing in the days preceding the event. The similarities to our current solar configuration are striking, both occurring during solar maximum periods, both featuring unusually large coronal holes in nearly identical positions. More recently, the March 28, 2025 Myanmar earthquake, magnitude 7.7, occurred precisely during the 7th rotation of our current persistent coronal hole. This wasn't an isolated event. It triggered what seismologists call a global seismic burst, with 3 additional magnitude 6 plus earthquakes occurring within hours across different regions. The worldwide response pattern suggests a truly global mechanism connecting solar activity to Earth's crustal dynamics. But what exactly makes these coronal holes so significant for earthquake potential? The key lies in understanding their unique properties. Coronal holes are regions where the sun's magnetic field opens outward rather than looping back to the surface. This configuration allows solar plasma to escape at much higher velocities than normal, creating what scientists call high-speed solar wind streams. These streams have 2 critical characteristics: extremely high velocity, often exceeding 650 kilometers per second, and anomalously low plasma density. When these streams reach Earth, they create complex interactions with our planet's magnetic fields, ionosphere, and potentially even the lithosphere itself. Analysis of solar wind data during major earthquakes reveals a consistent pattern. Seismic events often coincide with periods when solar wind plasma density drops to extraordinarily low levels, sometimes below 0.1 particles per cubic centimeter, compared to the normal 5 to 10 particles per cubic centimeter. This creates what plasma physicists call an osmotic gradient between space and Earth's interior. Think of this as a pressure differential that may actually draw plasma from Earth's internal regions towards the surface and ultimately out to space. If this plasma movement occurs across fault lines, it could effectively reduce friction by breaking molecular bonds, allowing stressed faults to suddenly slip, triggering an earthquake. The scientific evidence connecting solar activity to seismic events continues to strengthen. A detailed analysis of 2024's largest earthquakes revealed that virtually all coincided with significant coronal holes in Earth-facing positions. The single exception occurred during a powerful G4- geomagnetic storm, another solar-driven phenomenon that creates profound electromagnetic disturbances in Earth's upper atmosphere and potentially its crust. What's particularly concerning about our current situation is that we've recently experienced both conditions simultaneously. A G4 geomagnetic storm just days ago, combined with its persistently growing coronal hole now approaching Earth alignment. The lingering effects of that storm may have already primed Earth's geophysical systems, making them more responsive to the upcoming solar wind changes expected from April 22nd onward. As we examine the historical distribution of magnitude 8.5 plus earthquakes since 1900, we can identify the regions at highest risk, primarily subduction zones along the Pacific Ring of Fire, where oceanic plates dive beneath continental plates. Japan, Alaska, South America's west coast, and the Cascadia region of the northwestern United States all contain fault systems capable of producing catastrophic events when triggered. The convergence of these multiple risk factors, Earth's overdue status for major earthquakes, a persistent and growing coronal hole approaching Earth alignment, recent geomagnetic storm activity, and the current solar maximum phase, creates a situation demanding close monitoring over the coming weeks. While the statistical correlation between coronal holes and major seismic events provides compelling evidence for a solar-earthquake connection, understanding the underlying mechanisms reveal an even more fascinating story. The key to this relationship lies in the unique properties of solar wind streams emerging from these coronal holes. Unlike normal solar wind, which maintains a relatively consistent density of 5 to 10 particles per cubic centimeter, the plasma ejected from coronal holes creates extreme conditions. Extraordinarily high velocities exceeding 650 kilometers per second, combined with plasma densities that can plummet to just 0.1 particles per cubic centimeter. This radical departure from normal space weather conditions creates what plasma physicists refer to as an osmotic gradient between near-Earth space and our planet's interior. Think of this as a pressure differential in plasma concentration, a fundamental force that seeks equilibrium. When the solar wind's plasma density becomes anomalously low, it essentially creates a vacuum-like condition that may actively draw plasma from within Earth's interior towards the surface and ultimately out to space. This mechanism gains credibility when we consider that Earth itself is not the inert rock most textbooks portray. Mounting evidence supports the georeactor theory, the concept that Earth's core contains a natural nuclear fission reactor. This is not as far-fetched as it might initially sound. Uranium, being one of the densest elements, would naturally concentrate at Earth's center through gravitational differentiation during planetary formation. Once sufficient quantities accumulated, self-sustaining nuclear reactions would begin. The implications of this internal reactor are profound for earthquake generation. Nuclear fission produces numerous light elements and charged particles, effectively creating plasma deep within our planet. We see evidence of this in the mysterious helium emissions continuously detected from deep Earth sources. Traditional geology struggles to explain these persistent helium fluxes, as primordial helium should have escaped long ago given its propensity to rise. Active production through nuclear processes involves a more coherent explanation. This brings us to the critical question. If Earth is generating plasma internally through nuclear processes, and solar conditions are creating a gradient that draws this plasma outward, what happens when this plasma movement intersects with stressed fault lines? The answer appears to involve fundamental chemical and physical disruption of the fault itself. When plasma, essentially ionized particles, moves across a fault zone, it can break molecular bonds in the crystalline structure of rocks. This effectively reduces friction between fault surfaces by neutralizing the electromagnetic forces holding them together. It's somewhat like inserting a lubricant between two rough surfaces, but at the atomic level. Once these bonds are compromised, the accumulated stress in the fault can suddenly release, triggering an earthquake. Have you ever wondered why earthquake lights, those mysterious glowing phenomena reported during major seismic events, occur almost exclusively during the largest earthquakes? Could these be visual evidence of plasma discharges as this internal Earth plasma escapes through fracturing crust? Before answering the question, don't forget to subscribe to our channel. Make sure to hit the notification bell so you don't miss out on our daily videos. The electromagnetic dimension of earthquakes extends beyond visible light phenomena. Seismologists have documented consistent electromagnetic emissions preceding major earthquakes, with distinct radio frequency signals detected days or even weeks before large events. The Schumann resonances, global electromagnetic resonances generated by lightning discharges, show characteristic anomalies before significant seismic activity. These observations make little sense in a purely mechanical model of earthquakes, but align perfectly with the plasma interaction hypothesis. Satellite measurements have revealed another critical piece of evidence. Ionospheric disturbances systematically precede major earthquakes. The massive 2011 Japanese earthquake created measurable changes in the vertical total electron content of the ionosphere, essentially generating a massive electromagnetic pulse that radiated outward from the epicenter. Similar patterns have been observed for other large events, suggesting a direct electromagnetic coupling between Earth's interior and the upper atmosphere. The solar maximum phase we're currently experiencing amplifies all these effects. During solar maximum, the ionosphere receives approximately 1,000 times more X-ray flux than during solar minimum due to increased sunspot activity. This dramatically enhances Earth's global electric circuit, potentially increasing the plasma content in Earth's lithosphere and making the entire system more responsive to solar triggers. What makes the current situation particularly concerning is the convergence of multiple risk factors. The persistent coronal hole we're monitoring has survived 8 rotations since October 2024, growing progressively larger with each appearance. Its 7th rotation coincided with the March 2025 Myanmar earthquake and global seismic burst. Now, in its 8th rotation, having grown even larger, it threatens to create an extended period of anomalous solar wind conditions beginning around April 22nd. This pattern of successive coronal hole rotations, creating a cumulative effect, resembles what precedes the catastrophic 2011 Japan earthquake. In that case, multiple coronal hole rotations created a sequence of high-speed stream impacts visible in solar wind velocity data, with plasma density dropping to anomalously low levels just before the magnitude 9.1 event struck. The electromagnetic coupling between space weather and Earth seismic processes represents a paradigm shift in our understanding of earthquake triggering mechanisms. While traditional seismology focuses exclusively on mechanical stress accumulation and release, the plasma interaction model provides a framework that explains both the statistical correlations we observe and the electromagnetic phenomena that consistently accompany major seismic events. When we examine which regions face the greatest risk from the solar-triggered seismic events, subduction zones emerge as the primary concern. These geological formations, where one tectonic plate dives beneath another, create the perfect conditions for megathrust earthquakes, the most powerful seismic events on our planet. The Pacific Ring of Fire contains the majority of these danger zones, a horseshoe-shaped region encircling the Pacific Ocean, where approximately 90% of all earthquakes occur. Analysis of magnitude 8.5 plus earthquakes since 1900 reveals a clear pattern of distribution along these subduction boundaries. Japan's position atop multiple converging plate boundaries makes it particularly vulnerable, as demonstrated by the devastating 2011 Tohoku earthquake. The Cascadia subduction zone, stretching from Northern California to British Columbia, represents another high-risk area that has remained ominously quiet for over 300 years, accumulating enormous strain energy that must eventually release. The Chilean coast, site of the most powerful earthquake ever recorded, magnitude 9.5 in 1960, continues to experience regular seismic activity, indicating ongoing stress accumulation. Similarly, Alaska's southern coast, which experienced a magnitude 9.2 event in 1964, shows concerning signs of strain buildup along its complex network of subduction interfaces. What makes the current situation particularly alarming is our ability to monitor these risk factors with unprecedented precision. Modern space weather observation platforms have revolutionized our understanding of solar terrestrial connections. The Solar Dynamics Observatory, the SDO, provides continuous high-resolution imaging of the Sun across multiple wavelengths, allowing scientists to track coronal holes with remarkable detail. The Advanced Composition Explorer, or ACE, satellite positioned at the L1 Lagrange point between Earth and the Sun delivers real-time measurements of solar wind parameters, including the critical plasma density measurements we now know correlate with major seismic events. Ground-based magnetometer networks distributed globally capture the electromagnetic signatures of solar wind interactions with Earth's magnetic field. These instruments have repeatedly detected the characteristic patterns preceding major earthquakes, patterns we're observing right now. Ionospheric monitoring stations utilizing GPS signal analysis can detect the vertical total electron content anomalies that typically precede large seismic events, while specialized radio receivers track Schumann resonance perturbations that often signal impending crustal stress release. The integration of these diverse data streams represents a paradigm shift in earthquake forecasting capability. While traditional seismology relies primarily on historical patterns and ground-based measurements, this emerging interdisciplinary approach incorporates space weather dynamics, electromagnetic precursors, and plasma physics into a more comprehensive understanding of earthquake triggering mechanisms. What can individuals do with this information? First, understand that earthquake preparedness remains essential regardless of specific timing predictions. If you live in a seismically active region, maintaining emergency supplies, securing heavy furniture, and knowing evacuation routes represents prudent precaution. For coastal areas potentially affected by tsunami events, familiarizing yourself with warning systems and evacuation plans could be life-saving. For the scientifically curious, this represents an extraordinary opportunity to witness an emerging scientific understanding in real time. The current convergence of risk factors, Earth's overdue status for major earthquakes, a persistent and growing coronal hole approaching Earth alignment, recent geomagnetic storm activity, and the ongoing solar maximum creates a natural experiment testing the solar earthquake connection hypothesis. Conventional geology textbooks have traditionally presented earthquakes as purely mechanical processes, often overlooking the electromagnetic dimensions we've discussed. The plasma physics perspective offers valuable additional insights into earthquake mechanisms that complement rather than contradict the established mechanical stress models. The implications of the solar earthquake connection extend far beyond academic interest. If validated through continued observation and analysis, this framework could revolutionize earthquake forecasting. While precise prediction remains challenging, identifying high-risk windows based on solar conditions could provide valuable lead time for emergency preparations and potentially save countless lives. The current risk window, beginning around April 22, 2025, warrants close attention. The coronal hole's unusual width suggests an extended period of solar wind anomalies, lasting approximately 7 days. Based on historical patterns, this represents the type of condition that has preceded the largest earthquakes in recent history. The fact that this is the 8th rotation of this persistent and growing feature, with the 7th rotation already triggering significant seismic activity, raises the risk level considerably. Monitoring platforms like NOAA's Space Weather Prediction Center provide real-time data on solar wind conditions, including the critical plasma density measurements. As we approach this high-risk window, watching for the characteristic pattern, increased solar wind velocity, followed by anomalously low plasma density, will be particularly important. These measurements, combined with ionospheric monitoring and ground-based electromagnetic observations, may provide the most comprehensive early warning system yet developed for major seismic events. As we continue uncovering these profound connections between our Sun and Earth's seismic activity, we're witnessing science evolve in real time, the integration of disciplines revealing patterns that remain hidden when studied in isolation. If you found this exploration valuable, share this information with friends in seismically active regions who might benefit from enhanced awareness. And if you like this video, then you should check out our next video on the end screens of our natural disaster playlist. See you soon.